Okay.
All right. All right. So just for the sake of the recording, we're talking about the dominant pole before we go back to pole placement. So we're saying that if you had the s plus 1, s plus 2, s plus 10, then the poles are minus 1, minus 2, or minus 10. And that would lead me to have an output of a e to the minus t, that is for the first pole, e to the minus 2t, that's for the second pole, and ce to the minus 10t, that's for the third pole. And if we make a little sketch, what we are saying now is that the output is the sum of the values. So let us say that t equal 1 second. The output is let us say that this value here is 5, and this value here is 4, and this value here is 0.1. So output equal 5 plus 4 plus zero point 0.1. So that's 9.1. So what I'm getting at now is that these poles here, which is these poles here, the output, they are called dominant because they add the most to because they add the most to the output. Why? Their contribution is greater, right? Contribution is more. The contribution is more. So your textbook tells you that the dominant pole is the one that is um closer to the poles that are closer to the
Y-axis.
y-axis are the ones that are dominant. But um I don't think they do a good job of explaining why they are dominant. Right? Yes, because they are closer to y-axis. Then when you can calculate in the output, they give a bigger contribution to your calculation for your output. So um that is a little discussion about the dominant pole. We're going to need to have an understanding of what we mean by dominant pole when we look at this evening's aspect of pole placement. So we're going to take an example. Uh, yeah, this working. Yeah, will make my life easier. After all of that, it's going to make my life easier. And so I want to look at that problem. Now, you will observe two things, that the plant is a third order plant. So all the time that we have been working with second order systems. So what do we do when we have a third order system and we need two gains for the third order system? And somebody look on last week and um tell me what the formula that we had for. So we want the peak overshoot to be 10%, and we want the settling time to be 2 seconds. What the formula for peak overshoot again? And the formula for settling time.
Peak overshoot is e to the minus damping ratio pi over square root of 1 minus damping ratio squared.
Settling time.
4 over damping ratio omega n.
All right, and then let's say the damping ratio. If we wrote out the formula for the damping ratio was equal to what?
Omega n.
No, in terms of the peak overshoot.
Hold on. Ln squared peak overshoot over pi squared plus ln squared maximum peak overshoot.
All right, so we're going to determine the damping ratio now. So that is ln squared 0.1 over pi squared plus ln squared 0.1. Yeah, just realized that.
You know if you have the square root.
Yeah. All right, so much that work out. Calculator was here somewhere. We worked this out last week already. So somebody look and tell me the answer.
0.591.
All right, so we have the damping ratio. So omega n now is going to be damping ratio 0.591 times the 2 seconds. So 4 over 0.591 times 2. So what you get for that? I'm going to take up the calculator. I don't know which part to go. How much you get? Oh, teacher.
3.384.
3.384. Okay, so now our second order equation is Gs is equal to omega n over s squared plus 2 damping ratio omega ns plus omega n squared. So that is going to be equal to omega n, which is 3.384. We're not so concerned about the top, but the behavior is governed by the denominator. So that's 2 times 0.591 times omega n, which is 3.384 s plus 3.384 squared. That's 3.384 over s squared plus, so 2 times 0.591 times 3.384. What do we get for that?
4, sorry, 3.999, so 4.
4. And 3.384 squared.
45.
11.4.
1.
All right, so we work with 11.45. So this is what our system should look like. But the problem that we have is that fine, this is what the system should look like. Should be s squared plus 4s plus 11.45. But it's a second order system. So if we look here, we see that this is second order. But the problem that we had a third order system. So then what do we do? So let's find the transfer function of the system that we have here now. SQ1231. It's K1 plus K2s over s squared plus 2s plus 3s plus 1 all over g over 1 plus gh 1 plus k1 plus k2s over s cubed plus 2s squared plus 3s plus 1. And if we simplify that, going through all of the shenanigans, that's k1 plus k2s all over. So we're going to carry the s cubed, so that's s cubed. We're going to carry the s squared, that's plus 2s squared, and then k2s plus 3s, that is k2 plus 3s plus 1 plus k1. So we have a problem because this system is second order. And this system is third order. So what do we do? What we have to do is add another pole to, so we have to add another pole to the system up here. So we are saying add a pole but the pole that we add must not interfere with, because this is the transfer function that we have worked out for the second order system. Is the transfer function that will make the system behave in the way that we want. So what we say we do in this situation is that we find the poles of, so let me just write it down as notes now. So find the poles of So first thing we have to do is find the poles of our second order system. Our calculator. Somebody can use a calculator or the MATLAB and find the poles of that system. If you want to find the poles of that system using MATLAB, it's going to be, I don't have a campus-wide license yet, and I have to remove. So y is equal to roots of 1, 4, 11.45 to get what the poles are. But we can, whoever calculator, I can just put it in there. Me have the $500 Ginos calculator, so. Chinese knockoff of the Casio.
So we get the first one 3.38 at angle 126.
Tell me plus or minus, give me it in rectangular form now.
All right, hold on, let me convert. The answer is supposed to be complex, sir.
It's not supposed to be, it can be. If it is that a problem to us?
Minus 1.99.
So we'll say minus 2, right?
All right. Plus 2.73.
Okay. So the roots or the poles are 2 minus 2 plus or minus 2.73. So now what we do, so find a pole. Then what we are going to do, to add another pole. Which is at least 10 times the real part of the pole above. So therefore, that implies that we are going to add s plus 20 to our system. So our at least s plus, so because 20 is 10 times the 2 that is there. So what we are saying is that if we add this s plus 20 to our system, to our s squared plus 4s plus 11.45, then this pole, which is s equal minus 20, will not add very much to the system, will not affect the system very much. So that's why it is called pole placement now, because we are placing poles and each of them have their function. So we're going to make the system third order by adding a pole, which is at least 10 times.
Sir, what if the two poles are real?
If the two poles are real, it still don't matter. So suppose we got s plus 2, s plus 3. then that would mean our poles are -2 and -3. So then the pole that we'd be adding would be at least 10 times the dominant, -3. So the pole that we're adding, as we said, would be at least 10 times. So we'd add up another pole, -20, and do it same way. That this -2 is the dominant pole. So if the poles are real, we don't really care. All we're doing is examining the real part of the pole. Remember now, this part controls the oscillation, the frequency of the oscillation, and this part controls the decay. So we are adding a pole that decays very fast. So the transient on the S+20 is not going to affect the system by much. So that is what we are saying. So it doesn't matter if there's no oscillation. If the poles are real and there's no oscillation, fine. So we're going to take the dominant pole, the most dominant pole, and we're going to multiply by 10, at least 10, or 11, or 12, or 13, or 14, or 15. It don't matter. But at least 10. So for the purposes of this example now, so new system has characteristic equation S+20 times S squared plus 4S plus 11.45. And so we'll multiply that out. You're doing it by hand, but you can use MATLAB and do it. So that's S cubed plus 4S squared plus 20S squared, so that's 24S squared plus 11.45S plus 80S. 11.45 plus 80 is 91.45 plus 20 times 11.45. And that 20 times 11 is 220. All right, but preserve my brain cells. Don't know why I'm going to like my school challenge, please. So it's 22, 229. Check it for me, make sure say we don't write down any foolishness there. See if we get the same thing. Am I correct?
Every day I try to remember how to write it in a MATLAB. You know?
120 CONV 120, 11.45. Not sure this bracket is the right bracket, but yeah, there's an error that was made that I have to go and correct, but I have to wait until we reach. Up to where we reach, and correct it at that point. So when we reach up here, when we verify, then no, I make a deal with one thing that I should not have done that I did.
I'm getting an error. Getting an error in the. Well, I have 1,20
Mm.
and then bracket. It's telling.
Just type in CONV. You don't have it in front of me. I don't know if it's a square bracket is a problem.
I change the bracket.
Type in CONV, you know, boss.
Yeah, man, me have it in it.
No, it's it.
Invalid expression. It's saying that the 1,4. 1,4 is a problem. Alright, hold on. I can't remember. Still a problem.
All right, let me tell you what you have to do to correct it. Yeah, the MATLAB in front of me. Then I would have. But when going out to the schools, campus-wide license. Oh, all right. So let U be equal to the 1,4, no comma, and let V be equal to the. Wait, what we did that?
All right.
Instead of doing that, so U equal 120 and V be equal to 11.45 and then put con U V.
U equal to 1,20.
Yeah, not comma. Don't put in the comma.
Oh. So, but bracket though, U equal bracket 1.
Yeah, square bracket, please.
Oh, matrix. Okay. 120. All right. And then V.
The 1,4, 11.5. So U equal. Let me.
Okay. So did I try? Okay. Okay. 11.45. And then so conv
U comma V.
Yeah, this should work now.
Mm.
Yeah.
Yes, it work. You're right.
124, 91.45, 229.
All right.
Mm. All
All
right.
right. So my head still at work. All right. So now I made a little mistake. There's something that I left out that I should not have left out. So I'm going to go back now. Um, put, put it in because here's what happened. Each of these values should be corresponding to each other. The S's should correspond, but these two don't correspond. Everything else corresponds except these two. Or we can find a value of k that would make everything correspond. But we need to find a value of k. But the 24 and the 2, we have a problem. So here's what we have to do. We have to go back up here. Start from beginning. And correct everything from up here. So we have to have k1 plus k2 plus k3 s squared. There's a third order pole, so we need 3. If it work out to 0, fine, that's not an issue. So this would be k1 plus k2 plus k3 s squared. So therefore, the transfer function would work out to be s plus k3, sorry, 2 plus k3 s squared plus 3 plus k2 s plus 1 plus k1. So therefore, this down here would now be 2 plus k3 So therefore now we find the values of the gains for the system. So k1, 1 plus k1 is equal to 229. So that implies that k1 is equal to 228. K2 plus 3 is equal to 91.45. So that implies that K2 is equal to 91 minus 88.45. And then 2 plus K3 is equal to 24. So it implies that K3 will be equal to 22. So these are the gains. So the point is that if we have a third or higher order system, we just add poles until these two systems are equivalent, but we have to add poles that don't interfere with our work, and then the poles that we add that don't interfere with our work have to be 10 times bigger in magnitude, not sign, than the dominant poles for the system. So we're good with that?
Sir, scroll above it, please. Yes, sir, right here.
Right, then we can look at another example.
Sir, can I scroll back down, please, sir?
Sure. What the formula for peak time?
I over omega D.
All right. So have a go at this one for me now and tell me what. So have a go at this one. Right. We work out a value for the damping ratio yet.
Yes, sir. 0.69.
Okay. So the damping ratio is ln squared 0.05 over pi squared plus ln squared 0.05 square root of all of that. That's equal to 0. Pi over 5 square root of 1 minus 0.69 squared. What you get for that? How many that
0.868.
is? 0.868. So you're what you got for the poles of the system?
Minus 0.6 plus or minus 0.62J.
Minus 0.6 plus or minus 0.62J. That? Alright, so what is the pole that is added?
60.
6.
6.
So new pole is equal to S plus 6. So our characteristic equation becomes
Sir,
Mhm.
what is that word? Char, clar, what is that? CHAR? Char equation?
Characteristic.
Oh, character.
What is the transfer function of this system that we have? That K1 plus K2 S plus K3 S squared all over S cubed plus, what is the characteristic equation of this?
Sir, 1 minute, sir. For the characteristic equation, one time, MATLAB it, we get 1 S cube plus 7.25 S squared plus 8.25 S plus 4.5.
Well, we work with that. Go and tell me what it is again.
No, man, we get the same thing where sir get, man.
Oh, all right.
Oh, wait, make a mistake with a digit.
Careful, you know.
Okay.
Right, man, right.
All right. All right. So the characteristic equation, the transfer function of the system that we started out with, what was that going to be equal to?
Say that again, sir.
We want the transfer function of this thing up here, so this is S cubed plus K3 S squared. We want the transfer function here. This thing that we're looking at here. That's the transfer function of that.
So you just multiply them, sir.
You know, you have to use G over,
1 plus GH.
multiply them here, and then use G over 1 plus GH. So that is K1 plus K2 S plus K3 S squared all over 1 plus K1 plus K2 S plus K3 S squared over S cubed. This is supposed to be over S cubed as well. S cubed plus 2S plus 1. S cubed plus 2S plus 1. Now we simplify that, we're going to get S cubed plus K3S squared plus
K2 plus 2S.
K2 plus 2S plus
K1 plus 1.
K1 plus 1. And so we're going to compare the two characteristic equations. So we're going to compare this characteristic equation with this characteristic equation. So S cubed plus 7.2 S squared plus 7.95 S plus 4.5 is equal to S cubed plus K3 S squared plus K2 plus 2S plus K1 plus 1. So that is going to imply that K3 is equal to 7.2 when we compare both equations. K2 plus 2, 7.95. So subtract 2, that's 5.95. And K1 plus 1 is equal to 4.5. So K1 is equal to 3.5. So those are the gains that we would require for our system. All right. So any questions up to there? No. For next week's class, I am going to ask you to, well, suppose you have access to the campus-wide copy of MATLAB. So I need everybody to be in front of MATLAB. We are going to be looking at a few things. Observability, controllability, stability, and we're going to use MATLAB to do our pole placement design for us. So MATLAB can automatically do the pole placement design. So we don't have to basically do as much work. We can get the we still have to do some amount of work, but MATLAB will just do the calculations for us. So how much people in front of MATLAB presently?
Yes, sir.
The second.
Class should have access to MATLAB because we are using it in a DSP.
DSP.
So you have it in front of you presently, or you have access to it?
We have access to it, sir. Even presently too.
All right. So you say I don't have a little dilemma here. All right. So I know what I will do. Mr. Campbell,
Yes, sir.
you have MATLAB
Yeah.
working with presently. So I need to change the settings. See, I don't want to go up and then we lose. All right. You know what? There are other things that I want to do, but I will do them next week. We're going to be using MATLAB to talk about those things. Because I want to talk about state space, but I need to make this thing here marinate a little bit in your brain. So I don't want to talk about two different things in the same class session to switch our minds from that. So I'm going to pick up next week with the MATLAB and talking about observability, controllability, and those things. But we have to talk about state space and using MATLAB to obtain the state space equation for a system. And then after we talk about those things, observability, controllability, and stability, which you should have done in the control course as well. But most likely you're going to say, no, never seen it before. So we're just going to do the MATLAB version of all of those things next week. So make sure that next week you have access to MATLAB. All right?
Yes, sir.
All right. So we stop in there. We're going to stop here.
Yes, sir.
We're going to stop here.
Okay, sir. All right, sir.
All right.